Counting in Class 11 is about moving past lists and into logic. Success depends on a single decision made before you ever touch a calculator, asking yourself, does the order matter? Look at this red digital locker. If the code is 123, that specific sequence grants access. Punching in 321 triggers the alarm. The positions of those numbers define the outcome. When order is critical, you are working with a permutation. Now look at this blue bowl. If you drop in an apple then a banana, or a banana then an apple, you have the same fruit salad. The sequence doesn't change the group. When order is irrelevant, you are looking at a combination. Identifying whether you need a position for a permutation or a collection for a combination dictates which mathematical path you take for every problem that follows. This logic relies on translating two simple words, and or, into mathematical operations. In this wardrobe layout, if you need a shirt and a pair of pants, you multiply the independent choices. 3 shirts on top, pairing them with 4 pants below, gives you 12 possible outfits. But if the choice is exclusive, meaning you pick a shirt or a dress, you add the choices together. 3 shirts plus 2 dresses equals 5 total options. Determining whether your options compound through multiplication or stay separate through addition is the required baseline for the formulas we're about to use. This is the formal permutation equation, but for now, look past it. Focus instead on this visual approach: 3 empty red slots. If you need to arrange 3 people into these 3 chairs, you multiply the available choices as you fill the spots. 3 choices for the first slot, 2 for the second, and 1 for the third. 3 times 2 times 1 equals 6 arrangements. This works until a restriction is introduced, a limit on the environment that prevents a standard formula from working. If we have 7 people to seat across 5 chairs, but 2 seats are broken, you must isolate and lock down those forbidden elements first. We remove the broken seats and calculate the remaining paths using only the viable slots. You adapt the math to fit the physical constraints of the problem. Manipulating the environment, the slots, rather than forcing a rigid formula is how you master complex permutations. Combinations use a different formula. The key difference is this extra r factorial in the denominator, which acts as a duplicate eraser. Consider a room with 10 people where everyone shakes hands with everyone else exactly once. How many handshakes take place? Apply the order test here. Does the sequence of the people in the handshake change the event? When 2 people shake hands, A plus B is the same as B plus A. Because the sequence doesn't matter, this is a combination. To find the total, we take our 10 people and multiply by the 9 others they could each shake hands with. That gives us 90 pairings. But since every handshake was counted twice, we divide by 2. This leaves us with exactly 45 unique greetings. Knowing when to divide out those duplicate arrangements is what separates rote memorization from actual problem solving. Let's test this with a final scenario. You have a stack of 5 distinct books, and you need to choose 3 to pack into your bag. Does the order of the books inside the bag matter? Use that answer to pick your formula, calculate 5, choose 3, and leave your answer in the comments. To summarize, a specific position is a permutation. Think of the red locker keypad. A collection is a combination. Think of the blue fruit salad bowl and divide by duplicates. Finally, handle physical restrictions first. And means multiply, or means add. Counting is no longer about listing numbers. It's about using this decision-making framework to solve any scenario you encounter.
Success in Class 11 math often depends on a single choice, deciding whether the order of elements actually changes the result. Look at this red digital locker. If the code is 123, entering 321 leaves it locked. Because the sequence matters, we call this a permutation. Now look at the fruit salad on the right. Whether you add the apple or the banana first, the resulting mixture is identical. Since the order of entry has no effect on the outcome, this is a combination. Permutations define strict arrangements where position is key, while combinations describe flexible selections where only the members of the group matter. Once you identify the grouping, you apply the fundamental principle of counting. If you need a shirt and pants, you multiply the options. If you are choosing between a shirt or a dress, you add the options. Memorizing this and multiply or add rule provides the logic needed to navigate the multi-step problems found in advanced exams. Friction usually occurs when a problem introduces an at least condition.
This often leads to the mistake of trying to force every variable into one massive equation. Consider this. Form a 5-person committee from 12 people, containing at least 3 seniors. A single multiplication fails because at least implies several paths. Sorting the pool into seniors and juniors makes these paths clear. Rather than solving for one group, we treat the at least condition as a prompt to identify every individual scenario that satisfies the rule. This tree maps 3 ways to satisfy the rule: 3 seniors and 2 juniors, 4 seniors and 1 junior, or 5 seniors. For the first path, we need 3 seniors and 2 juniors. We use the AND rule, multiplying their individual combinations. Since order doesn't matter for a committee, we calculate the combinations for 3 seniors from the senior pool and multiply by the combinations for 2 juniors. When working within a single required grouping, the requirement for both parts to exist simultaneously means you must multiply. Pause the video now and try to write out the combination math for the second path: 4 seniors and 1 junior. The setup requires the combinations for 4 seniors multiplied by the combinations for 1 junior. We complete path 3, calculating ways to choose 5 seniors and 0 juniors. With totals for 3 independent branches, the final committee can be path 1, or path 2, or path 3. We add these totals together for the final answer. This simulation tests the same logic. You need to form a 4-person team from 6 boys and 4 girls, and the team must contain at least 2 girls. Start by identifying the distinct team harpositions that satisfy the requirement of having at least 2 girls. Apply the multiplication rule to find the totals for each individual team composition. Then determine when to use addition to find the final result. Post your step-by-step logic in the comments to show how you mapped the scenarios and which operations you chose for each step. Counting without listing every possibility relies on recognizing whether you are arranging items in a fixed order or simply selecting them as a group. This cheat sheet summarizes the core rules for permutations, combinations, and the fundamental principle of counting. Use these 4 quadrants as a reference for your next practice set.
Hit subscribe to simplify your syllabus. And turn on notifications so you never miss a splash.